Hello, welcome to the second part of the video introduction to Module 5. This video will cover the material in section 5.2, which will help us learn to make confidence intervals and find p-values using normal distributions. In our last video, we said that the sampling distributions, bootstrap distributions, and randomization distributions that we simulated in chapters 3 and 4 are normal distributions and can be modeled with a normal density curve. But not all bell-shaped distributions are normal. Normal distributions have to have a particular density. And so the question becomes, well, how do we know that these are actually normal and not some other bell-shaped distribution? There is a theorem called the central limit theorem that is perhaps the most important theorem in statistics, which tells us that for random samples with a sufficiently large sample size, the distribution of sample statistics for a mean or proportion is normally distributed. So, central limit theorem says we need sufficiently large sample size, and so we say, well, okay, how large is sufficient? And that depends on the situation that we're working in. We'll hear more about this in Chapter 6, but sort of just generally speaking, if we're working with a quantitative variable that's not super skewed, then a sample size of at least 30 is usually big enough to have a normal sampling distribution. And if we're working with categorical variables, as long as the count in each of the categories is at least 10, then that is usually a large enough sample size to be sufficient. When our sample size is sufficiently large and we want to make a C% confidence interval, it doesn't have to be 95%, it could be any percentage of confidence we want, we can use a formula based on the normal distribution. And what we're going to see is that we're going to use a formula that looks very similar to the formula we used back in Chapter 3 to make confidence intervals. Before we had the sample statistic, or our point estimate, plus or minus 2 times the standard error. Now instead of taking the statistic plus or minus 2 times the standard error, we're going to take the statistic plus or minus z star times the standard error. Now you probably remember that the reason we used the number 2 times the standard error was because the 95% rule told us that 95% of sample statistics will be within 2 standard errors of the parameter we're trying to estimate. Z star here is a value that we are going to find using StatKey. It depends on the level of confidence that we want to have in our interval, and it's going to be chosen to give us that level of confidence that we want. If we're looking at the standard normal distribution, Z star is going to be the value that's going to cut off the middle C% of the data. So if we put C% of the distribution in the middle, it'll be between negative Z star and positive Z star. And this is going to give us C% confidence in our confidence interval. There's a separate video to show you how to find Z star using StatKey, so make sure that you watch that. So just to summarize where we're at so far, we want to make a confidence interval, C% confidence interval. We are going to be using our sample statistic plus or minus Z star times the standard error. The statistic comes from our original data, remember. Z star we're going to use from the standard normal, we're going to use StatKey to get that. And the standard error is something that so far we've only seen how to find it using the bootstrap distribution to simulate it. For now, when we're working with, in this section 5.2, usually we're going to be given the standard error. And the reason that we're doing this is because we're going to later on learn some formulas that we can use to calculate the standard error without doing simulations. But for now, most of the time, the standard error in this sort of part of the course is going to be just given to us until we learn those formulas. And we'll start to do that actually in Chapter 6. Okay, so let's do an example. In May 2016, the Gallup organization asked a random sample of 1,022 U.S. adults, do you approve of the way Congress is handling its job? Of those sampled, 184 said that they approve. the standard error is 0.012. See, that's just kind of given to us at this stage. We're going to give a 90% confidence interval for the proportion of all U.S. adults who approved of the way Congress is handling its job in May 2016. We're going to use our formula for the confidence interval, statistic plus or minus z star times the standard error. Okay, so first thing we're going to need is we're going to need to figure out what our statistic is. Here, since we're estimating a proportion in the population, our statistic is going to be the sample proportion. So our sample proportion, p hat, we find by taking 184 who approved divided by the total number gives us 0.18. The z star for 90% confidence is 1.645. We'll stop for a second and look at where that came from. Here we are in stat key. We're going to go to the theoretical normal distribution. We're using the standard normal, so we're going to check that our mean is 0, yes, and our standard deviation is 1. Yes, that's the z distribution. Now we want to put our confidence level, that proportion, in the center. So 90% confidence. To put a certain proportion in the center of the distribution, we use the two-tail option. And now I'm going to change this proportion in the center to 0.90 for 90% confidence. And the z star value is down here. It's the cutoff on the bottom, 1.645. So there's our z star. That's where that came from. The standard error was given to us at 0.012. So plugging into our formula, we get a confidence interval that goes from 0.160 to 0.200. And to interpret it, I'm 90% confident that between 16% and 20% of all U.S. adults approved of the way Congress was handling its job in May 2016. So there's an overview of how we can use normal distributions to make confidence intervals. Next, we're going to talk about making hypothesis tests using the normal distribution. So hypothesis tests and p-values, if the randomization distribution is normal, then where before we were finding the p-value as the proportion of dots in the appropriate tails beyond the observed statistic, now instead we can find the p-value as the area in the appropriate tails of the normal distribution that is beyond the observed statistic, using a normal distribution that is centered at the hypothesized value, the null value, and has a standard error that is the standard error of that randomization distribution. So to think about this, if this is our randomization distribution, before in Chapter 4, we say, okay, well, where's my observed sample statistic? I was finding it. And then for my p-value, I was looking at the proportion of dots that were further from my hypothesized value than my sample statistic. So I was looking at the proportion of dots out here. Now we're modeling this with a smooth curve. And instead of looking at the proportion of dots out here, we're going to be using, instead, the p-value will be the area under this normal distribution. Now we saw in the last video that when we're working with normal distributions, the area beyond a certain point in a normal distribution only depends on what the z-score is of that point. So instead of using the normal distribution that's centered around the hypothesized value, we could also find the p-value by finding the area in the appropriate tails beyond the z-score of our observed statistic in the standard normal distribution. And this is how people actually do a hypothesis test working with normal distributions, is by calculating the z-score. We have a special name for that z-score that we calculate. It's called the standardized test statistic. So we calculate it by taking our statistic from our sample, we subtract off the null hypothesized value, and then divide by the standard error. Once we've calculated the standardized test statistic, we will use the standard normal z distribution to find the p-value. Let's look at an example. In a random sample of 501 U.S. adults, 216 believe that children should stop trick-or-treating before they turn 13 years old. The standard error for this estimate is 0.022. We want to know, is there strong evidence that fewer than half of U.S. adults think that children should stop trick-or-treating before the age of 13? And we're going to test at the 5% level of significance. So the first thing we need to do is we need to make our hypotheses. Now, since we're interested in one categorical variable, whether people believe that children should stop before they turn 13, we're going to be interested in a parameter that's going to be a single proportion. So, our hypotheses, we want to know, is there strong evidence that fewer than half then is our alternative hypothesis, p is less than half, less than 0.5, and our null hypothesis, which remember always has to include an equal sign, is going to be that p is equal to 0.5. The next thing we need to do is we are going to use our data to calculate our standardized test statistic. So we use our formula, z equals our statistic minus the null hypothesized value divided by the standard error. Our statistic in this case is our p hat, 216 over 501. There's our p hat, our sample statistic. Our hypothesized value, 0.5, comes from the null hypothesis. And the standard error, remember, is given in the problem. Once we do the calculations, we get a value of negative 3.13. Now, one thing to be careful of when you're typing these things into your calculator is to make sure that you put parentheses around the top, because if you don't, it will use order of operations and it will do this division here first and subtract the whole thing from your p hat. So just make sure you use your parentheses. Now that we have our standardized test statistic, we're going to need to use the standard normal distribution to find our p-value. Just to kind of remind us, we have a less than sign in our alternative hypothesis, which means we're going to be doing a left-tailed test. So we're going to go into stat key and do a left-tailed test with our standardized test statistic of negative 3.13. So here I am in stat key. Once again, I'm going to the theoretical distribution for the normal. I'm going to make sure I have the correct mean and standard deviation. For the standard normal, that means a mean of 0 and a standard deviation of 1, and those are right. Now, I said I'm doing a left-tailed test because my alternative hypothesis is that p is less than 0.5. And my standardized test statistic was negative 3.13, so I'm going to change my cutoff to my standardized test statistic. And now my p-value is given up here. So the chance of seeing a sample proportion as extreme as the one that we observed, or more extreme if the null hypothesis is true, is our p-value, 0.00087. Now, since our p-value is less than our 5% level of significance, we reject the null hypothesis. And the last thing we need to do is make a conclusion. In this case, there is strong evidence that fewer than half of U.S. adults think that children should stop trick-or-treating before they turn 13. Now, the only sort of missing link here is that in the last two examples, in both of them, we just had to be given the standard error. But how would we know what the standard error is if we weren't given it? And it would be nice, wouldn't it, if we could compute the standard error without doing thousands of simulations. And what we're going to find in the next video, and in Chapter 6, we'll focus on this, that when certain conditions are met, we can. There will be relatively simple formulas to use to calculate the standard error in a variety of different situations. So that's what's coming up. Thanks. Have a good day.